In this video, we're going to discuss my favorite descriptive statistical technique used within statistical storytelling, and that is the inclusion of graphics. It's interesting because graphics show a lot that's difficult to say numerically, or as most people think of it, statistically. A lot of people don't really consider graphics as a statistical technique, and in some ways they're right, in some ways they're not. Ultimately, graphics are summaries of information that are used to describe what has happened, which places them within the classification of descriptive statistics. It's important to recognize that through showing a lot that's difficult to say, graphics have a unique contribution to make on top of just descriptive or inferential statistics, which is why I place them in their own category, even though when I think of them as a descriptive statistical technique. One common rule of thumb when I'm analyzing data is to look at the graph of the data as a first step. And again, it's because graphics show so much information and in such convenient formats that it's really important to be able to see this as early as possible. This is a great way to identify things like outliers or things like weird patterns in the data. There's a famous example, actually, of a series of data sets with two variables, x and y, looking at the relationship between them, where they have the same relationship. It's a series of four data sets. All four have the same relationship between x and y. All four have the same average x score and the same average y score, etc. And for all intents and purposes, the statistics for all four show the same data. But when you actually look at the data sets look extraordinarily different. These four data sets are famous because they do a very good job at exemplifying why statistical graphing is an important contribution within your broader statistical story. And it's because sometimes what graphs show are things that are difficult to quantify, even though they might be easy to see, and on seeing them, they might even be easy to describe. Now, I love graphics a ton. In fact, again, they're my favorite statistical storytelling technique, but they do have some limitations. The first is they're up to interpretation. And you could think that a difference is big and somebody else could think it's small. You could think a relationship is strong. Somebody else could think it's weak. So with this, when I'm using a graphic, it's important to realize that different people may look at the same graph and have different takeaways or different interpretations of that. And that's a limitation of the graphics. It's a place, honestly, where our statistics, either descriptive, if I'm just looking to describe numerically the measure of the relationship, or if I'm looking to test inferentially whether the relationship is there in the population level, that the statistics can come into play, is to make this less subjective. But at least in base graphics, this can be pretty objective. Reverse that. Statistics are more objective in base graphics. They are more subjective, What's another thing? So when we're looking at graphics, we could see relationships. Graphics don't really address, though, could this have just happened by chance? Remember, that's what our inferential statistics test. Graphics don't have any comment on that. And so it's important, if you're looking at if there's a relationship or not, or if there's a difference or not, to include inferential statistics to tell that part of the story, because graphics do not speak to that part of the story. One last detail, or one last limitation, is the loss of specific detail. So sometimes in graphics, they can do a really good job at showing big picture stuff, and often that's what we need. But sometimes it's tough to find fine detail. If you think of the height of a bar chart, I don't know exactly what that number is. If you think of a point on a scatter plot, I might not know the exact coordinates of that point. So depending on the graphic, this loss of detail could be more or less, and depending on the research question, this loss of detail might be more important or less important. But it's important to remember that this is a limitation of graphics, broadly speaking. So in this lecture video, what we're going to do is we're going to go through several different graphics, and we're going to talk about some of the strengths, some of the weaknesses within these different graphics. This is by no means an explanation of all graphics, nor are the examples provided here. I kind of pulled up a few things. I did a few in a couple of different softwares, and I kind of threw them together to exemplify particular points of the graphics, but these aren't perfect graphical representations of data either. In fact, some of the best graphical representations of data are custom jobs for particular data sets and particular stories that they're trying to tell. I think all of the best exemplar graphics are custom graphics created for that. So there's a lot of room for creativity with graphical creation, and there's a ton of room for storytelling. It feels like every time you think you've maxed out the amount of information a graphic can portray, there's one more thing you could add in there. And so ultimately, graphics can be extraordinarily efficient ways to tell a statistical story. And so we'll talk about some of the ways that we can do that, some of the good ways and some of the bad ways that we can do that. Here. All right, histograms. So in their base form, histograms are used to show the distribution of a single continuous variable. And by distribution, just think like which of the scores are people most likely to have. Or so let's use an example of age. So histograms would be used. Age is continuous. You can have any age in a certain range. And the distribution of age, we're just saying, well, in our sample or in the group that we're studying, what are people's ages? So we'll have an x-axis that's going to focus on the ages that people could have, and then the y-axis that's going to focus on how many people are at that age. So I might have an x-axis value of 30 and a y-axis value of 100, indicating 100 people have 30, 100 people are age 30. Now, when we make histograms, we have a whole bunch of different bars representing different ranges of data. So I'm not going to have a single number. In ages, I might have 10 to 20, 20 to 30, 30 to 40, 40 to 50. So I might have these ranges. And one key decision when making a histogram is how many bars should I have? Should I break it up by decade? Should I break it up every 5 years? Should I do it every 2 years? And why? Now, I will say often we select between 7 and 20 bars to subdivide the data just to make it usable. Sometimes we'll go a few more, but not too many more, maybe up to 30. The trick is that if we have too few, then it's not going to be particularly descriptive. But if we have too many, then it's also not going to be particularly descriptive. In a similar way that we discussed the balance give and take with our confidence interval, the confidence percentage. Too small versus too many, both can be bad. Here, too many bars, too small bars, both can be bad. Now, I will say, we will talk about briefly a method where we can kind of extend the bars to infinity and make a continuous distribution. It's called a density plot. It's not really what's going on, but it's kind of a feel for it. And that can be a useful representation too. So in this case, the height of the histogram represents the counts for that range of the particular bar classically. Now, I will say that this is the classic example. We'll talk about some modifications on the next slide. One common confusion is between histograms and bar charts. Histograms are made for a continuous variable. Bar chart is the same type of chart, but is made for a categorical variable. So I would make a histogram for age. I might make a bar chart for sex, and a bar chart will have just 2 bars, one for male, one for female, or male, female, other. Age, I would have that continuous range of ages, and then I'd do particular chunks of ages that I'd want to study. So, depending on the story that we're telling, we can change the basic histogram. So, we already talked about changing potentially the number of bars. We can do this to better illustrate the range of interest. And we can, I'm trying to think, grades is the only example I can think of. Maybe instead of having equally sized bars, I want to do A, B, C, D, and F. So 90 to 100, 80 to 90, 70 to 80, 60 to 70, and then 0 to 60. So a different width of bar. This could be useful in that particular case. Of course, maybe it'd be better to just report it A through F and report it categorically using a bar chart too. But changing the number of bars can have a large impact in the story that our graphic is telling. The other thing that we can do is change the scale of the y-axis. So traditionally, histograms will have counts on there, how many people fall within each group, how many people are between ages 20 and 30, how many people, and that's the height of the bar for 20 and 30, how many people are between age 30 and 40, that's the height of the bar between 30 and 40. But sometimes we'll do instead probability or density, which is kind of like a probability, but relates to how close the counts are, broadly speaking. And in this case, probability is sometimes more useful. In fact, I'm trying to think, it probably is more often than not more useful because it's just so broadly applicable. Typically with counts, we can use counts for, I guess I've got another line here. Typically with counts, we can do counts when like the total sample size is very well known, and so the count has a meaning. So if I tell you we're 20 people less in this group, that means something to you. But more often than not, it's easier to say 5% less. Percent is more generally applicable and requires a little less specific knowledge. So again, all of these depend on the story you're trying to tell and the context in which you're telling it and the audience you're telling it to. So use the one that's easiest to interpret. But in my opinion / experience, percentages probably are easier in terms of specific numbers. On the other hand, in a bit of a weird way, when I put percentages on the y-axis, that tends to confuse people. So they like to see numbers on the y-axis depending on what the numbers are. So it kind of depends on the context. It kind of depends on how the numbers are falling out in the plot. But don't forget, this is still part of your story, and you still have decisions to make with how you're going to tell this. The last thing I can do is introduce colors. I can do colors to break the graph down by categorical variables. So let's say I want age for males and age for females. I could do males as red and females as green, and I could break I could put both of those graphs on the same graph to kind of show the distinction between them. In our example we're going to talk about in a second, I think I look at the outcome variable, which is number of polyps, and look at the number of polyps based on the treatment group and the control group and put them both on the same graph to see which one has more and which one has less. And just like before, I can do these colors with the percentages. So I can say, this many % of people have this. Normally, when the percentages are done, it's % within the group. So that if there's unequal group sizes, if I did % of total population, unequal group sizes would show disproportionately on a graphic. So it's percentage within the group to show proportionally within graphic. I'll say maybe one other thing regarding that, like when I'm reporting descriptively kind of information on, say, counts or percentages, I'll often do both. Like for male, female, I'll often report, 25 males, that's 15% of the population, and 180 females, that's whatever % of the population. So I'll often do both sample size and percentage together. All right, well, let's look at some examples. So again, the examples we're going to talk about, this is a data set on 12-month follow-ups on a polyp treatment, and we're going to be plotting the number of polyps. Now, for these graphs, for full disclosure, these are made in a different statistics software than Excel. Some later in the lecture we'll use in Excel. But some of the ones at the end of this are not possible in Excel. So here, the scale of the x-axis, that's the left to right horizontal one, is number of polyps. You see my bars that I was talking about earlier. And again, the height of the bar represents the number of counts within that particular range. Now, I can change the number of bars if I want to, as we talked about before. Here, this number of bars, I think this is 30 different intervals, some of which have 0 in them. So you'll note that some bars have a height of 0. Now, this can give some more information. So previously, I saw a broad bar that went a little bit below 60 to well above 60, maybe 60 to 68, and I had 2 individuals fall there. Here, I can see a little bit more detail there. I've got 2 individuals, but both are just above 60. None of them are below 60 in terms of the number of polyps. So the more bars give more detail. On the other hand, you'll see the average height of the bars shrink, and you'll see a lot of bars with just a single person in there. And that indicates that there's just one person in that grouping. So that can be a little less informative, and the end game with that is if you have enough bars, all of them will be of height 1 and not really tell you very much at all about the data. Now for the y-axis, recall the y-axis can represent counts, or it can also represent densities or percentages, depending on the context I'm looking in. So densities can be useful in a case generally where we can interpret those percentages. And this is probably a little bit more broadly applicable than when we can interpret the counts. Now, again, I say quote unquote that if we increase the number of bars, continuously, we can kind of connect them with a line, and that makes this curve. That's not quite what's going on. This is called a density plot, and it is a kind of a big brother to the histogram. Ultimately, what it does is it creates percentages, but it creates percentages based on our density of our data. So ultimately, it'll ask, well, how many data points are within blank range of any particular point on this curve? And that's where it'll draw its height. So this is not the same thing as making infinite numbered bars in a histogram. All of those would just have a single entry in them. It'd just be a flat line if I connected them all. This looks at something maybe a little deeper, which is sometimes useful and sometimes not, but these can be very handy and are a pretty elegant way to illustrate your data. Sometimes I'll see it both ways. I think density is probably a little bit more inferential in nature because it's smoothing out. Again, in our actual counts here, you'll see that there's some counts like above 20 that have 0. The density plot is saying, well, maybe I didn't observe anything there. It just means it's less likely, but there's probably people in there because of the continuous nature of the variable. So it's a give and take with a density plot. We're not going to go too much into this in this class. They suffice it to say they serve a similar purpose to histograms and can sometimes look pretty fun. Doing a little bit more advanced version, I did it with density plots because it looks kind of cool, is we can add those colors. So here I have the placebo group and the drug group. Placebo is in red, drug is in this blue teal color, and I have them overlaid on the same plot. So I can see that those in the drug group had much less polyps at the end than those in the placebo group. The placebo seemed to be roughly balanced between 0 and 60 polyps at the end, whereas in the drug group, we had most of the people were right around 0, maybe a little bit more, and then we had a few people between, say, 20 and 40 polyps. Nobody above really 40, it looks like, given our density plot. So this can be a great way to illustrate a point. In this case, a point I may be trying to illustrate is the drug looked like it was effective at treating the polyps in the patients. Now here, I want to be careful. Graphics are a useful aid in statistical storytelling, but they can be misleading. So consider, what if I put this graphic out which again seems to show, if we're reading this, that the drug group had less polyps than the placebo group. But after doing inferential statistics, it turns out that I can't conclude that for the population. Like, this might be true for the sample, but I don't have enough evidence to make this claim for the population. What does providing this graphic do? Well, ultimately, this is very misleading. And I have to be really careful when presenting something like this if this isn't supported statistically. So if I were doing something that maybe this difference wasn't supported statistically, maybe I would present the base graphic without that split and say, look, we don't have enough evidence to determine that there's a difference between drug and placebo. This is what the number of polyps look like overall. Or maybe I could present this, but I'd have to be really, really, really clear with my audience. You cannot use this as evidence regarding that the drug is more effective, because we don't know. This could have just happened by random chance. And in fact, in this particular case, given all the preceding factors, this could have happened by random chance. And so it's important to make sure that you're articulating this and potentially choosing to select a different graphical representation of the data than this graphical representation based on your inferential statistics. So graphs are extraordinarily powerful tools, but don't just drop in pretty ones. Make sure that all of your story is aligning. That is, your inferential statistics should support your decision-making in terms of what graphic you select. And in this case, again, may help me determine between presenting one that's broken out by subgroups that are, in fact, different, or presenting one that's not broken out by those subgroups. Similarly, if my subgroups were the same and the graphic indicated that the subgroup, or excuse me, let me rephrase. We don't test if they're the same. We test if there's not a difference. Similarly, if there wasn't a difference between my subgroups and my graphics demonstrated that there wasn't a difference between the subgroups, then what I might do is present the graphic because that graphic aligns in terms of what it looks like and what it implies with what my inferential statistics are saying. So what I'm saying is make sure that you are telling the story of your data and that you're telling it consistently. So if there's not a difference, make sure you're not presenting a graphic that makes it look like there is, and vice versa. All right, bar charts. So as I mentioned before, bar charts are essentially the same plots as histograms. The only thing that's different is that the x-axis is categorical rather than continuous, which means that instead of having a whole bunch of bars next to each other, I'll have different categories, and each categories are going to have their own bar. Now in bar charts, we separate each of the categories, or each of the bars, excuse me, with space. And part of the goal here is to indicate that the x variable is not a continuous variable. It's a categorical variable. So this isn't that these bars run against each other and they're a continuous spectrum. No, this is category A, category B, category C, and they are all completely distinct from one another. Bar charts are really useful at comparing values between different categories. And we'll have some cool stuff we can do with them that we're going to talk about in just a moment. And again, the main distinction is ultimately that x-axis, that it's categorical with bar charts and continuous in histograms. Now, what's weird with bar charts is even though these are so similar to histograms, these actually have a lot more flexibility. The reason is because within the category, if you think about it, I can do the counts within the category, but I can also do some other stuff within each category. Now, with a continuous variable, the bars are really relegated to be counts or percentages. But in the bar charts, in addition to what we did with histograms, I can do things like using heights to display different quantities than counts or percentages. Maybe with male and female, instead of using the height to display how many individuals are in each, I look at average number of polyps within each. And that's something that I just can't really do in a histogram. I can also stack bars to indicate proportions within multiple groups. What proportion within females was assigned the placebo? Finally, I can use clustered bars to kind of draw comparisons between subgroups. Now, this is similar to adding color to our histogram where I put two on the same. And so it's kind of counts, but the look is going to be a little bit different because of the categorical nature of our x-axis. And so it's going to, the term for this will be clustered bar charts. So let's dive into some examples. Now, these are all made in Excel, and again, are pretty straightforward. You'll note that my some of my axes are not particularly nice to see, so I apologize about that ahead of time. So again, basic bar charts look very similar to histograms. We've got female, we've got male, we've got the height representing the counts. In this study, we have 9 females, and we have 13 males. I could also, if I wanted to, put percentages on the y-axis instead of counts, depending on what we're looking at. The cool part, though, is I could do different quantities than just counts. So note here that the height of the bars no longer represents the counts within each group or the number of people. In this case, it represents something different, the average number of polyps in each group. I'll note that what this does is this changes our 1 variable situation to a 2 variable situation. In the previous graph, I had a single variable, male and female, and then I was counting how many times that variable occurred. Now I have 2 variables. I have the sex of the participant, male, female, and then I also have the count of polyps shown on the y-axis. So this is now a graph of 2 variables, even though the graphical structure hasn't changed. And again, this gives us some more flexibility with these bar charts and is not really possible to do in a meaningful way with histograms. Now, I'll also note quickly the scale of the y-axis. This is not our main focus, but is worth probably chatting through because it's a way that we can be deceptive with graphics, and we don't want to do that in our statistical storytelling. So note that the bottom of the y-axis, it ends at 21.5 as an average. And because of that, it makes this difference between female and male look rather stark. Look at this graphic. If I change the bottom scale to now be 0, you'll see that the difference between male and female is not anywhere near what it looked like previously. The difference looks much, much smaller. Now, which graphic is right? Well, probably this one, but it is occasionally acceptable to change the scale of y as long as you make really clear, be very open, notification to your audience. You could use maybe the minimum value of polyps as your bottom. In this case, the number would be 0, but you could use the minimum. You could go up to the maximum. So that would be using the range as the scale of your y-axis. That would communicate some additional information in a graphic. That would add not only variable A and variable B, sex and number of polyps, but also would communicate the range of the number of polyps potentially, which could be useful. But again, it also depends on your research question and your story. So let's say, going back to this graphic, maybe a distinction of 3 is actually meaningful. And so here I have male peaking at around 23. I've got female approaching 26. Maybe this scale is important because of the clinical significance of this distinction, and that would drive my scale selection. Note what I've done, which is let Excel auto-choose, is almost never the right decision. I really should be making an active decision based on this. If in doubt, make sure you have 0 on the scale. If 0 is a reasonable number, or at least the minimum in the data value on the scale. And if you have a clinical or practical reason to have a particular size, then maybe make that the scale so that you can clearly articulate whether or not this met the standard of clinical or practical significance. Again, goal is just to think through the question deeply, try to illustrate what the data are telling you related to the question. And remember, this isn't to find a graph that proves your point. It's to tell the story that's going on in the data. Here, there is a distinction, but neither of these groups are close to 0. And in this case, because 0 polyps is a reasonable outcome, 0 probably should be on this scale. Now, consider a bad way of storytelling. Let's say instead of looking at this, which is average number of polyps in each group, I looked at the sum of the polyps in each group. In the males, we have about 275 polyps in the male group. In the females, we have a little more than 200 in the female group. Well, clearly this looks like males have way more than females, whereas this one looks like, oh my gosh, females have more than males. The story is very different. And you might say, Dr. Florin, how can this be? Statistics is broken. We can never know anything, etc. But the truth is, again, these answer different questions. Now, this is easy to navigate if you start with a question and you're trying to tell the story of the data easier. But if my goal is to convince my readers that males have more polyps than females, this can be very deceptive. This is such a fine line to walk. And again, walking the line of trying to observe what's going on in the data and trying to study that and trying to tell that story, that really helps to clarify how we approach issues like this, where I have two seemingly at odds graphics, and perhaps I'm not sure which one to present. So it's important to realize that when this kind of thing happens, usually what's happening, almost always, unless something absolutely bizarre is going on, almost always, these are answering two different questions. The first one is answering the question, what is the average number of polyps per person within each subgroup? This is answering the question, what is the sum total of polyps within each group? If you're looking at one graph and expecting the other, you might have an unexpected finding and need to dive deeper. Why does this look like the way it was? And going back to the original graph, let me see if I can pull this up quickly here. Here's our original graph. Why might I expect more polyps to be in the male group if I just added up how many there are? Well, looking at this, I have more males than females in my sample. So if I just took all of the males and added up the number of polyps for them, I'm going to expect there to be more in the male group because there are more males. So which graph is right? Well, it depends on your question. It really, really, really does. There's a funny article about the religion of statistics as practiced in medicine. Maybe that's the article I should make available for our class this week. Where the priest, the statistician, asks the devotee irrelevant questions like, why did you run the experiment? And what is your research question? These seemingly trivial questions. And these are questions that people get frustrated with during the design phase of a study, are extremely important when trying to make a decision between graph A and graph B, which tell very different stories. Because they are different stories, they're slightly different research questions, but maybe with completely different answers. And this is why being really specific about the question that you're asking at the front end is important. Were you trying to study the total number of polyps, or were you trying to look at the average number of polyps per person? There could be good reasons for both. I think the average number of polyps per person is probably the most common thing you're probably trying to study. But without the initial rationale of the study, we don't know which graphic is more honest. And again, it's not even, I don't have any skin in this game. You know, Dr. Florin, presenting this in our class lecture, I got no skin in this game. Which one should I present? Well, I don't know. Without knowing the original question, I don't know which one is better. If your goal is to biopsy a bunch of polyps and understand what options you have, the sum graph might be more honest and useful because you can see that you have more options in the male group, which is true. You have 275 options to pick from in the male group, and you've only got a little over 200 to pick from in the female group. And maybe that's the real use, and that's what I need to display, and this graphic is a lot more honest. Now, this is probably a function that we have more males than females in the sample. But again, if the goal is just the number of polyps, that really doesn't matter. In fact, more people is just all the better. That means I've got more opportunities to pull these from. On the other hand, if my goal is to show which group has individuals who are maybe more susceptible to polyps, then maybe this graph with the average polyps per person is more meaningful. And ultimately, that would let me compare if treatments are working at an individual level, et cetera. So there's all this to say, look back at your research questions. figure out what is my research question trying to ask, what is the purpose, and then try to match the graphic to that purpose. Where does this get bad? This gets bad when I'm trying to prove my point. I am looking at average number of polyps per person, and then I just happen to stumble across this graphic. Oh, I know that average number of polyps per person looks like this, but this one just looks so much more like what I'm trying to tell. Dr. Flora, this is really my story, not because the data told me, but because this is the story I wanted to tell from the start. And that's where this can get risky. And that's where statistics can be extraordinarily deceptive. So again, I just encourage you to really consider and check yourself on the mindset. We had a massive lecture on this to start this lecture set. And this is one of the places where that can come out. So really, really visit through the issues raised in that. And as part of statistical storytelling, really focus on the goal, really focus on the research question, and focus on telling the story of the data as it relates to that research question. All right, moving on. So in addition to regular bar charts, another thing we can do with bar charts is to stack on top of each other. And really what this is doing is this is taking our original count bar chart and subdividing it into groups of drug and placebo. This is great to be able to show comparison. So here I can clearly see there's less females than males. We can do group comparisons, like there's less placebo in female than in male. Like we can see that in terms of a count. It's not necessarily clear if that's proportional or not. So we can do these proportional comparisons, and that's also available with a standardized stacked bar chart, where we put the proportions within each group, female and male, as 100, and then look at the proportions within each of them. So I can clearly see now, yes, the female has has a higher proportion of drug than placebo in comparison to the male group. Female has less percent placebo, but actually that difference actually looks less than it did in this original chart. Females looked like they had about half of the placebo in this chart, but at least part of that was due to the fact that we just had less females overall in our study. And so this demonstrates the proportional differences between each of these can be useful in different situations. Again, refer back to your research question and the story you're trying to tell. Last, we can look at clustered bar charts, and this is helpful for comparison. So typically, I use clustered bar charts when trying to compare based on the grouping. So here, I can see in females that the drug group is working way better than the placebo group, and I can see in males the drug group is working better than the placebo group. So here, I'm showing that comparison between drug and placebo within my different groups, and this is how I break that down. So we can also switch the groupings. So I can instead, if I wanted to highlight comparisons between males and females, I can switch which variable is on which axis. So I can make male, female my colors and placebo, drug my x-axis. Let's do that here. And now I get a different comparison. Within the placebo group, females have more polyps than males on average. But within the drug group, females have less polyps than males on average. So note that this is, again, changing the comparison. With clustered bar charts, I cluster with the colors. The colors are the thing that is most easy to compare, and the x-axis then is the context. So I'm comparing male to female in the context of placebo, male to female in the context of the drug. And in the previous graph, I was comparing placebo to drug in the context of female, placebo to drug in the context of male. So what's interesting here is that this shows that males had a lower average number of polyps than females for the placebo group, but not for the drug group. And this is kind of an interesting finding, or is it? Again, this is one of those things where we have a graphic that's showing something, but do we know if this is true for the population or not? So we really need to know which pieces of these graphs are just quirks of the sample, that is random chance things that really aren't indicative of a population effect, and which ones are indicative of trends in the population. If we don't have evidence that this is anything more than a quirk, it might be really bad to call attention to this in a report, to say, hey, the drug looks like it's way more effective than females than males. That would be bad to call attention to, again, unless we have the ability to indicate that that's true in the population or not. On the other hand, if we do have the evidence to do that, this is a great graphic to show that while the drug may be effective for both males and females, as we saw before, and we can do a statistical test for that and should before we make that claim, the drug seems to be more effective for females. And we can test this. For whatever reason, females in the drug group have virtually no polyps, while males in the drug group had a moderate amount of polyps in terms of this data set. So again, it's important to remember that our stories that we tell with the graphics should tie in closely with the story that we're telling with our inferential statistics. And we don't want to be deceptive by presenting graphics that tell stories that are not supported by inferential statistics. All right, the box and whisker plot. Now, this surprises a lot of my students because I talk about this in our most introductory of stats classes. But the box and whisker plot is one of my favorite plots ever, along with its new cousin called the violin plot, which is just a mirrored density plot. But this is a fantastic graphical tool. It uses a box around the quartiles with lines connected to the minimum and maximum, or occasionally we'll exclude outliers. They'll be written as dots on there, and the lines will be connected to the min and max, excluding the outliers, sometimes called hinges. In any case, the box plot is really, really handy because it can be used in similar ways to how we were talking about the bar chart just a second ago. So it's a great summary of continuous data in general. Maybe not quite as detailed as a histogram, but it's really nice because it can be used in the ways that we were just using the bar chart. So it's a kind of a blend between the two in some ways. From my perspective, when we use it in that form, it is better than the bar chart because it shows more. The bar chart just looked at the center, or in the ones we were looking at, or the sum or whatever. The bar chart just looks at one statistic, that measure of central tendency. And in a box and whisker plot, though, we get to look at multiple. We get to look at the measure of central tendency, yes, but we also, because we're making a box around the quartiles, and recall the difference between the quartiles and interquartile range and measure of spread, we get to look at spread too, and we get to look at skew. We get to look at a whole ton of different things within the box and whisker plot, or in the violin plot with which is just density, that is not available in the bar chart. So I really, really like using box and whisker plots in this context. So we can do a basic version. Now, box and whisker, because we're using quartiles, just needs ordinal data. Now we can do it with continuous data and do all the time. But we can also add some complexity to this. So consider grouping similar to the bar chart, and we can do something similar with box and whisker plots. So we can do the categorical axes, we can do the clustered groups, and we can do those with box and whisker plots as well. And again, rather than just the bar, we do a box and whisker plot within each category / subcategory, which show more information than just the height of the bar at a mean or a sum. It shows, again, depending on the chart we're using, the mean, the median, the spread, etc. So I want to highlight quickly the issues that the box plot can help with in addition, on top of the bar chart. So I want you to consider two plots, one of a bar chart and one of a box and whisker plot. So for the bar chart, I want you to consider something. Assuming statistical analysis backs up the visual implication, does it look like, and I should be careful what we're plotting here because this has changed a little bit. So we have the number of polyps at 3 months and the number of polyps after 12 months of follow-up. Does this look like time is related to the number of polyps? That is, does it look like there's a difference between the number of polyps at 3 months and the number of polyps at 12 months? If we take this at face value, if statistics support this. And if you're thinking about this, you can pause and take a second if you need to. I hope you'll say, yes, yeah, it looks like 12 months is less than 3 months in both the placebo group and in the drug group. All right, and you'd be exactly right. If statistics backs that up, then we can say, oh yeah, well, 12 is less than 12 months. We have less polyps in 3 months, even in placebo group. And this might strike you as weird. Like, we had a bunch of polyps and they just went away on their own in a placebo group. So that might strike you as a bit weird. Okay, so anyway, that's the interpretation of this bar chart, or the story that this bar chart tells. Now let's look at the box and whisker plot correspondingly. Looking at this box and whisker plot, I think you see an interesting finding here. What you see is that there's a couple of outliers that are really driving high scores, and they're not driving high scores across the data. They are just driving high scores at 3 months, and there's one in the drug group and one in the placebo group. So the conclusions made with the bar chart doesn't change per se, but we get a ton more context and information here, namely that there's some serious outliers that perhaps we should consider studying. Now, in this particular case, let's say we run through our outlier checks, and we've got a whole slide on what outlier checks I would run. And let's say we found out that these individuals had alternate interventions due to their high number. And so we end up defining that as a classification that should be removed from our study. Our study is only looking at individuals who have had the drug or placebo for this effect. And so because these outliers have had other drugs for this effect, because of the severity of their case, they should be excluded from the study. So let's look at what this looks like with those individuals excluded now that we've investigated that they should be. Consider my first question. What happens over time in the bars? What is the range over time? And we kind of agreed just, 2 minutes ago, that it looks like there's a drastic decrease, or not drastic, we didn't say, we just said there's a decrease in the number of polyps over time. But now that we've removed individuals who shouldn't have been in our study anyway, we can actually see that the opposite trend is true, that just from a couple of outliers, we have a very, very, very different average trend. And this is shown in both the box plots, and this is shown in our groups. Now, I should say, actually, this is kind of confusing. The placebo group is on the left side here, and it's on the right side here. So I apologize about that. And the drug group is on the right side here and the left side here. So I apologize about the differing numbers. It wasn't intended to throw you for a loop. It was intended to demonstrate, again, we've got a very different story. What's our news story? Well, the news story is that the polyps go up over time if not treated, but they don't go up very much if you're in the drug group. Of course, we still have maybe an outlier that's worth investigating, and in fact we did, and it's just a part of our sample. But if we remove that outlier, it would look like the 3 month would go down even further. So maybe this movement wouldn't be as neutral. Maybe it would still be a lot of movement up in the drug group as well, maybe limiting drug effectiveness evidence. But at least in terms of our bar chart, we're seeing a very different story. Again, in terms of our box and whisker plots, we're also seeing a very different story than what we saw earlier. Now, I will say, in the box and whisker plots earlier, this pretty clearly showed these look like, definitely not like massive decline from 3 to 12 months. These look like maybe staying stable from 3 to 12 months. Whereas in our box and whisker plots now, not stable, it looks like there's a bit of an incline, but you're seeing much less shift than we were seeing in our bar charts. This is a reflection of the mean versus the median. box and whisker plots are made based on interquartile range, and the median, these bar charts are based on the average in terms of the mean. All right, all of this has a point, I promise. How did we find out that there were outliers that we should consider? Well, we found that out by using a method that demonstrated outliers, that showed us more than just the center of the group, or in this case, the subgroups. It did more than tell us just the center or average. It also showed us the spread, the box and whisker plot. That's how we found that this was even something worth investigating. The utility is relatively similar to what we're seeing in the bar charts. But again, it has a lot more flexibility and conveys a lot more information within the same amount of space. I mean, the square footage for this graph and the square footage for this graph are about the same. But in this one, we are seeing a lot more information because we're incorporating not just information about center, but also information about spread. Now, this is not to say that box and whisker plots are the best and we should never ever use clustered bar charts or anything like that. This is to say that I really like box and whisker plots. I do. I really like them. I think they're pretty handy. And I like that they demonstrate this additional information. And so I do tend to recommend them when possible. They're probably one of my favorite tools for illustrating continuous outcome data by group. I do this if we're comparing 3 groups, then we'll just have 3 sets of box and whisker plots. We can do this subdivided stuff, do different colors for these clustered box and whisker plots. They're just a really, really, really handy tool for graphically representing data. All right, so let's close up our discussion of graphics here with a discussion of scatter plots. So scatter plots can help to demonstrate relationship between 2 continuous variables. Now, previously, we had histogram for a single continuous variable, and then we could add a categorical variable to it via color. We had a bar chart, which was a categorical variable on the x-axis. Then on the y-axis, we either had the count of that categorical variable or we added a continuous variable, which is very often done so that we have 2 variables, one categorical and one continuous. Categorical on the x-axis, continuous on the y-axis. Then we had box and whisker plots, which can do a single variable summary like the histogram, so it can be just for a single continuous outcome, or it can very easily be broken down into categories like the bar chart. So we talked about how we can implement these clustered box and whisker plots very, very similarly or analogously to the bar chart. So we've had categorical and continuous variables mixed together. Scatter plots are about 2 continuous variables or more continuous variables. Ultimately, we assign a variable, usually the independent variable in a study, to the x-axis and the other variable to the y-axis. You can do 3D scatter plots. Those tend to be difficult to interpret, even on a computer, but they look really cool. Still, interpretation is kind of a pain with 3D scatter plots unless the strength of the relationships between variable is very strong. And if it is, then 3D scatter plots can be really cool. But if it's not, then it can be kind of difficult to interpret. On the other hand, we should follow our story. If our story is looking at the interrelationships between 3 sets of continuous variables, then maybe we do need a 3D scatter plot. In any case, the vertical axis, whether it's the y-axis in a 2D or a z-axis in a 3D, is typically the outcome, the dependent variable, and the other ones, in our 2D case, the x-axis is usually the independent variable. To make a scatter plot, we simply find the x and y pair for each person. So maybe it's weight and height. I think in this example, I'll do the polyps at 3 months and the polyps at 12 months. The 12 months is my outcome, so that'll be my y, and then 3 months, that's my independent variable, seeing if I can predict polyps at 12 months using the polyps at 3 months. So that'll be my x-axis. And then I'm going to place a dot at the appropriate place on that graphic representing the independent, dependent variable scores. So if, let's say somebody had 10 polyps at their 3-month checkup and 5 polyps at their 12-month checkup, then I would go over to 10 on the x-axis and go up to 5 on the y-axis, and that's where I would put my dot in a scatter plot. Now, these are pretty basic tools. I'm sure you've seen these kinds of things before, but these are actually extremely valuable when looking at continuous data. There's a way that we can, depending on the statistical software, look at scatter plots for every pair of continuous variables when exploring data. And this is really great for finding relationships. Now, again, I'm not going to present these relationships as if I found them or as if they're really important or do any inferential statistics on them. But I can say, hey, look, I found this. This is what we should study next, or this is a relationship we should check out. I can also, if I'm ever a priori planning to assess multiple continuous variable relationships, check that out in this way too, where I look at a bunch of graphs that break these things down one at a time. So scatter plots are just an extremely valuable tool. They're used all the time with continuous data, looking at these types of relationships. Now, similar to before, I can add a little bit of color to spice these up and break them down by group. So I can add, if I've got a plot between two continuous variables, a categorical variable to that plot via color, which can help a lot. All right, so let's look at just a couple examples. We're not going to talk about too much crazy stuff with scatter plots. So here's an example of a scatter plot. X is the number of polyps at 3 months. That's our horizontal axis here, and Y is the number of polyps at 12 months. I'll note that this is with the outlier removes. You know, we talked about in the previous graph that maybe we should remove the outliers because they aren't part of the study. I'll just assume that this is building on top of that, on top of that theory. So this doesn't have those in here. And you can see that as the number of polyps at the 3-month follow-up goes up, typically the number of polyps at the 12-month follow-up also goes up. So if I'm out here at 30 polyps in the pre, or at the 3-month follow-up, I'm going to have more polyps at the 12-month follow-up than if I had 5 polyps at the pre, or I'm going to have maybe less polyps at the 12-month. So it looks like that as X goes up, my Y also goes up. Now, I'm about to break this down by the drug versus the placebo. What I'd like to see is that if you had 45 polyps at the 3-month, if you keep taking the drug, maybe by 12 months you'd have 0. So we'd like to see kind of a flat line here or a really low line if the drug seems to be working, or maybe just a lower slope, which would indicate lower 12-month polyps for a comparable 3-month polyp. So maybe we've got 50 polyps at pre. Maybe my placebo group is up in a 60 polyp or 50 to 60 polyp level. Maybe my treatment group is between 25 and 20 and 30. So maybe it doesn't completely eradicate them, keep them next to 0, but maybe just slows the rate of growth. It gets rid of about half of them, so that whatever my placebo group is, my drug group would be about half. So let's look at what actually happens in this data. So looking through this, you can see the drug group is now the light green spheres with the darker green outline. I can see that actually the rate of growth largely seems to mimic what is going on in my placebo. So after accounting for the polyps at 3-month, the polyps at 12-month don't really seem to change much. Yeah, it doesn't look in this case, and I've only got 2 real cases that are setting this pattern. That's important too. Got a lot of cases clustered down here that started with a very low number of polyps and ended with a very low number of polyps. But here, where I'm looking at the cases of individuals at 3 months who had polyps, or had greater than 10 polyps, there's only 2 cases in the drug group that even look at this, and both of those don't really seem to fare much better than what I would have expected a placebo group to do, based on the relationship between 3 and 12 months polyps for the placebo. On the other hand, there's some information here. So maybe here I have maybe if there's less than 10 polyps, the drug works really well. And then if there's more than 10, then maybe the drug's just not effective or not at a sufficient dose or something like that. So maybe this, less than 10 polyps, I've only got 2 placebo data points to compare to my drug data points. But both of these placebo data points seem to have increased in a way that the drug hasn't. Now, is this probably enough to be statistically significant? Absolutely not. So I would not be able to make this comparison and say, hey, look, if I wouldn't be able to say if the polyps is less than 10, the drug is effective. That is not supported with this data. What I can say is here's a weird little pattern. This is probably just an artifact in the data. But if this is clinically meaningful, then maybe we could run a little study to see if this has legs to keep going. Maybe if we gathered another 10 participants, maybe the inclusion criterion is that they have less than 10 polyps, and we balance them between placebo and control. We can see, is placebo hovering around 30 polyps? Is control still hovering around 1 or 2 polyps? And is placebo hovering around 30? Is treatment hovering around 1 or 2? And if so, then in that particular case, maybe we have enough data to justify a larger study and a larger study and a larger study. So this is kind of a weird thing. Honestly, this is probably an artifact of just the sample. So it's probably not an underlying population theme. Again, I want to be very clear when I say this to not indicate that, and just to say, if I'm hunting for something, the way that I would hunt for something is to say, hey, look, this is going on. This happened with our sample. I don't know if this will happen again, but we could test and see if this does happen again. And that could help us determine if maybe this is a drug dosage issue, maybe this is a drug effectiveness but only for a certain subpopulation of patients, those with lower levels of this condition, if that is the context in which the drug is effective. All right. So let's summarize. There's a bunch of different types of graphics. We just looked at a few. We really did. There's an infinite number of graphics. Again, a lot of them are custom jobs. My favorite ones have taken days to put together, and they have been very custom, very specific for particular situations, but they have been amazing. They have so much information on them. Sometimes I can combine graphical elements with inferential statistics elements, with different descriptive statistics elements, and I can include them all in the same graphs. A lot of fun stuff you could do. But in the base graphs that we talked about, we looked at most of them descriptively and gave the warning that, look, if you're going to demonstrate these descriptive differences, or if you're going to use a graph that highlights a descriptive difference, make sure you have the inferential data to back that up, or the inferential analysis to back up that there actually is a difference. If not, consider choosing a different graphic that doesn't erroneously highlight a difference that we don't have information to support. Graphics can incorporate a lot of information. And again, there's a lot of creative ways we could do it. Just in this lecture, I think we had an example. I can't remember which one it is, but we had where we said the scale of the y-axis, maybe we could make that the range of the data. That's a really subtle thing, but also informative. There's just so many ways to pack information in graphics. And so there's a lot of creativity that you can use to figure out, how could I add one more piece of information here, and what other piece of information could be added in. So we talked about really using our research question to guide which features of the data should be highlighted graphically. So where should what should I be highlighting? Should I be highlighting this difference between the groups, or maybe not? We also talked about how we can use inferential statistics to help with this, and really should use inferential statistics to help with this. I think that's a later bullet point on the slide, but it's an important component when we're highlighting features of the data. Graphics are fantastic at highlighting particular things. And again, you've got a virtually infinite number of graphics you can select to highlight a virtually infinite number of different comparisons. The question is, which ones do you select and why? And what I encourage you to do is, again, select the ones that are supported by the data inferentially. So graphics can be suggestive, but they're not necessarily conclusive. This was one of our warnings that, we talked about a couple examples that can be falsely suggestive. So, this looks like a really big difference, but maybe this difference isn't supported inferentially. We looked if there's a difference in the population, and we don't have the evidence to claim that there's a difference in the population. Maybe that's a sample size issue, maybe that's an effect size issue. But either way, we don't want to use graphics to tell a story that isn't supported. So we want to, if that's the case, if a graphic is really highlighting a large difference, but we don't have the data to support that there's a large difference, maybe we need to choose a better graphic that, again, it tells the story of the data. What are the data telling? And if the data aren't telling the story that there's a population difference there, then we shouldn't use a graphic that tells that story. We should use a graphic that tells the story of what are the data telling us. One other thing we talked about is that color is your friend. Color is your friend, and not just for style. I've seen in many of these graphics, adding color lets us add information. It adds another variable, another categorical variable to the graphs. Again, we should only do this when it's relevant, but these things are often relevant. If nothing else, we can look at differences between sex on outcomes. We can look at differences between races on outcomes. Maybe there's particular diagnostic classifications or employee classifications or hospital classifications that we can break these further down by. And it's a really easy thing to just drop in color, if you don't already have it, to add that additional piece of information. As we said before, if the graphic is deceptive, maybe we choose to not do this. Not that it would be wrong, but it would offer a lot of counterintuitive explanation. Hey, it looks like there's a big difference here, but actually the data don't say that. Like that would be a very difficult thing to say. But when it's right, it can be extraordinarily impactful to have that demonstrated. With this said, and I hate to walk this back because color is so useful, but if your research questions are not focused on those breakdowns, or if those breakdowns are not the story the data are telling, or if those breakdowns are not the story that answers the research question, then maybe don't do them because they would distract from the bigger issue, or maybe do them as an aside with your main graphic not having that breakdown, but highlighting the key issue. The goal, and I talk about packing information into graphics. I apologize because it's a bit deceptive. The goal isn't necessarily to see how much information you can pack into a graphic. The goal is to tell the story of the data and to answer the questions that your study set out to answer as clearly as possible. Now, if you can add additional information into there to give more context, to provide additional subsequent information, then absolutely do it. But if that is distracting from the main purpose of the graphic or the main purpose of the story that you're trying to tell, then don't distract from your own main purpose. Stick with the basics and then build up as needed or as available. All right. So the goal here, as with everything else we've been talking about in this lecture set, is to tell the story. So keep telling the story. Graphics are a very useful tool with regards to telling the story. They are my favorite tool in statistical storytelling, but it's important, again, to use them in conjunction with the other tools and techniques that we have talked about, those inferential statistics, the descriptive statistics, and the broader story that the data are telling. So this will end our graphics video. In the next video, we'll be ending this lecture set, at least as far as the lecture slides are concerned, by discussing the implications that study design can have on your statistical story.